Video. Welcome back, everybody. Last time when we were talking about clustering, at the beginning of our discussion, I showed you an example where we had data that looked something like this, maybe, oriented something like Mickey Mouse. And I said that depending on what algorithm you used, you might end up seeing different clusterings. So one approach, for instance, that might feel very natural to many of us is to think about each of these sort of circular regions as each being a different cluster. But if we were to use k-means on this type of data, that's not what we would necessarily see. So imagine that our cluster centers, for instance, are even at the centers of these different circles. Then we're assigning points to clusters based on which cluster center they're closest to. And so points like this, for instance, would be closer to one of the ears than to the center of this one. And so we'd end up getting clusters that might look more like this in red. And so this is not necessarily something that's intuitive to us because it's not necessarily adapting to the geometry and structure in this data set. And so today we are going to look at an alternative to k-means. There are many different clustering algorithms out there, like we've discussed. But the one that I want to focus on today is the expectation maximization algorithm. And there's several reasons why I think this is the right method for us to explore today. In part, it's going to give us an example of soft clustering. So it's a different paradigm than we saw with k-means. In addition, it's going to allow us to start thinking about probability distributions, and especially the Gaussian. So if you were to go on and take additional machine learning classes, after this one, you would start to see probabilistic concepts and probability distributions playing a much bigger role than what we have explored in this particular class. And this is going to give you an idea of just one of the different ways that we might see this manifest and one of the distributions that is particularly useful in many different settings. Okay, so with that, I want to start off by just taking our attention away from clustering for a moment and just talking about Gaussian distributions. Boy, I guess the glare is touching two boards now, isn't it? Maybe this will be okay. Okay, so with a Gaussian distribution, we are going to start with a distribution function p of x. And this is going to tell us, for a point x, how likely it is to occur under this distribution. So I'm going to write down the equation, and then we're going to unpack it a little bit and look at some examples of it. So in particular, we are going to have in an exponent negative 1/2 x minus mu, where mu is going to be the mean or the center of the distribution. We'll talk more about that in a second. Sigma inverse times x minus mu. And sigma is the covariance matrix here. And then we want to make sure that this, as a probability distribution, integrates to 1. So if I were to look at all of the different possible x's and all of the different values of the distribution function and integrate across all x, it should integrate to 1. And so to have this be properly normalized, I'm going to have 2 pi to the p over 2 power, where each x is in p dimensions. And the determinant of sigma, square root, where the determinant is just equal to the product of the singular values. Of sigma. Okay, so we're not going to talk about how to compute the determinant beyond the product of the singular values. But this is the expression for a Gaussian distribution in p dimensions, whatever value of p you want to use. So within this expression, so first of all, there's some shorthand. So we will often write this as sort of a curly or calligraphic n, and then in parentheses, we would have mu for the mean and sigma for the covariance matrix. And if you know those two parameters, then you know everything you need to know about this expression here. So this is a shorthand that we will use a little bit in this class. Within this expression, mu is equal to the mean. So if I were to draw an infinite number of x's from this distribution and compute their average, that would end up being mu. Sigma is a matrix, and the mean is also p-dimensional, the same dimension as x. Sigma is going to be a matrix, and it's going to be p by p. This is the covariance matrix. And it's going to tell us how the how different elements of x vary relative to one another. So in particular, I said before that mean was the expected value of x. So if I were to take an infinite number of x's from this distribution and average them, that would be the mean. So I, for the expected value, would use this notation block E of x. And I mention this because I'm not going to use that same expected value notation here. And if I were to look at the ijth element of this covariance matrix, it corresponds to the expected value of xi minus mu I times xj minus mu j. So if I were to draw, again, an infinite number of x's from this distribution, then I could look at two different coordinates, I and j, subtract off their means, and then multiply them together to see how big they are relative to one another. And this is going to give me the ijth entry of my covariance matrix. Okay, so to make this a little bit less abstract and hopefully more intuitive, I want to show you several examples. So for our first example, we are just going to work in one dimension, and I'm going to have mu equal 0 mean, and I'm going to make a plot as a function of x of this distribution function p of x. And this is the classic sort of bell-shaped curve that you have seen before, probably, like this. And now sigma, in this case, this matrix sigma is actually just a scalar, and we would typically write it sigma squared, and we would call this the variance of our variable x. And it's basically telling me what the spread is of this bell-shaped function. So I could alternatively have this same distribution, but with a larger variance, a larger value of sigma. Sorry, I'll use a different color. Okay, so this orange curve would be corresponding to a larger value of sigma squared or a larger variance, and this taller, narrower curve in white would correspond to a smaller covariance or a smaller variance or a smaller value of sigma squared. And so when we've got a smaller value of sigma squared, the values are more concentrated around the mean. Both of these curves, if we were to integrate them from negative infinity to infinity on x, they would integrate to 1. But the maximum amplitude is different and the spread is different. Okay, so far so good? Okay, so now let's move on to thinking about these things in higher dimensions. So let's draw a picture now of a Gaussian distribution in 2 dimensions. So P is equal to 2. Again, I'm going to have mu be 0. In this case, it'll be a vector of zeros. And I'm going to consider the setting where sigma, my covariance matrix, is an identity matrix times a value sigma squared. Okay, so now if I want to draw this, there's 2 ways I could try to draw it. One is I could have my vertical axis P of x here tell me the likelihood or the value of this distribution function. It's going to be centered at 0 again because the mean is 0. And basically it corresponds to taking one of those bell-shaped curves and then just rotating it around the vertical axis. So the pictures, I think, on the online lecture notes are much easier to see and interpret than my drawings here. But think about this sort of bell-shaped curve that's going the same, that's been rotated around the vertical axis. So it's got the same spread in all directions. For me, it's a little bit easier to actually draw a contour plot. So what I'm going to draw here is a plot where one axis is the first coordinate, x1, and the other axis is the other coordinate, x2. And then what I'm going to draw are contours. So what I want to know is find all the variables or values of x where this distribution function p of x is constant. So let's just say it's equal to some value gamma. And then so if I were to fix one value of gamma and draw the corresponding contour, then what I would see would be a nice circle. And if I chose a different value of gamma, I would see another circle just with a different radius. And if I chose another value of gamma, I would see another circle. So why a circle? And in fact, in some of our future examples, we are no longer going to see a circle. So let's just think about that. So P of x, I'm sorry, I'm going to move over to the other board. So I'm not writing in the sunshine. So we said P of x is equal to 1 over 2 pi to the P over 2, determinant of sigma to the 1/2, e to the minus 1/2, x minus mu transpose sigma inverse x minus mu. And now we're interested in all the places where this is equal to some constant level gamma. So now what we're going to do to try to simplify this a little bit is to say, well, we're really interested in identifying the x's where this is equal to some constant gamma. And so this normalization factor out front isn't going to affect what values of x's give me the same value of my distribution here. And whether I exponentiate or not isn't going to make a difference. So what I'm going to claim is that this is equivalent to looking at all the x's where x minus mu transpose sigma inverse x minus mu is equal to some other constant gamma prime. Right? So if this value is equal to a constant gamma prime for all x's in some set, then this expression of my distribution will be constant and equal to some other value of gamma. So all I need to do to find a contour line is to find all the x's where this expression is equal to some constant gamma prime. So now what I can do is I can say, well, what does this expression look like for the specific example that we had on the left-hand board? And so mu is equal to 0 in our example, and sigma matrix is equal to a scalar sigma squared times the identity. And so what we have in this expression is x1, x2 transpose times sigma squared identity times x1, x2. And we're interested in all the x's where this is equal to a constant gamma prime. And this is equivalent to saying that x1 squared over sigma squared plus x2 squared over sigma squared is equal to some constant gamma prime. And now that we write it this way, this looks very much like the equation, well, it looks exactly like the equation for a circle, right? And so this is how we can derive, even without doing some numerical plotting, that the contours for this distribution are going to look like a circle when we have our covariance matrix being equal to a diagonal matrix where all the diagonal entries are equal to one another. Any questions so far? Yes? So the question is, what happens if mu is not equal to all zeros? And what would happen, actually, so mu is telling us where the center of this is. So if we had a non-zero mu, we would still have these circular contours. They'd all just be shifted over so that the middle of the circles are at whatever our mu vector is. Yeah?
Can you explain one more time, I guess, what each circle on that contour plot means? Is it just a probability?
So this blue circle is equal to the set of all x's such that p of x is equal to, let's just call it gamma 1. And the red circle is the set of all x's where p of x is equal to some other value, gamma 2. Sort of like an elevation map in geography, right? So it's just telling us all the different places that have the same elevation, where elevation is determined by this distribution function. Yes?
So here the mu and the sigma are like parameters of the distribution?
That's right.
How can we get them given a sample?
Okay, we're going to get to that in a little bit because that's going to be a core part of the EM algorithm, how to estimate mu and sigma from data. But for now, I'm trying to give you some understanding about what mu and sigma imply. Like if I tell you that your data is coming from a Gaussian with the mean mu and covariance sigma, how can you think about that? Once we understand that, then we'll talk about how to estimate them. Yeah.
And also here, the expression, it should be like 1 over sigma squared instead of sigma squared. Right?
Oh, thank you. Yes. Thank you. Thank you. Thank you very much. Okay, just in case anybody caught that, I had a little typo here. This should have been that we have 1 over sigma squared, not sigma squared. Okay, so for our next example, we're going to do something similar. So mu is equal to 0, p is equal to 2, and our covariance matrix sigma is going to still be diagonal, but it's going to have different diagonal values. So I'll have sigma 1 squared and sigma 2 squared. Everything else is the same. So now, if we were to try to draw a contour plot for this distribution, We can follow the same series of steps that we did over here in example 2, but what we would get is that a contour would correspond to all points where x1 squared over sigma 1 squared plus x2 squared over sigma 2 squared is equal to some constant value, gamma prime. So what's this an equation for? An ellipse, exactly right. So now, if we were to draw the contours of this distribution function, we will see a bunch of ellipses. So, contour plot of this distribution in 2D. Again, we're having zero mean. And in this example, here, I'll draw my contours first. So I've got a bunch of ellipses corresponding to different contours. And here I've got more spread in the x1 direction than I have in the x2 direction. So, for example, this might correspond to my covariance matrix being 4, 0, 0, 1. Okay, so this is telling me now, my diagonal entries, when sigma is diagonal, how much spread there is in the different coordinate axes. But these ellipses, they're not only ellipses, but they are coordinate-aligned ellipses. So the major axis is, all the axes of the ellipses correspond to directions in my original x-coordinates. Any questions so far? Okay, so now let's look at our final example. Again, P is equal to 2. Mu is still going to be zero mean. And sigma is going to be more general. So sigma is going to be symmetric. So remember that means sigma is equal to sigma transpose. And it is going to be positive, definite. Real blast from the past here. As we talked about before, what this means is that we can actually compute the eigenvalue decomposition of sigma, and we can write it as V lambda, V transpose, where V is orthogonal. Let's say V transpose V is equal to V, V transpose is equal to an identity matrix, and lambda is diagonal. Okay, so now trying to plot the contours of this distribution function for a general covariance matrix that's symmetric and positive definite is more complex. But the core idea is basically that we think about this V matrix as telling us how to basically rotate our coordinate system. And then the lambdas are telling us how much spread there is in the distribution in these different coordinate directions in our new basis. So if we were to plot our contours again, we might see something like this. So this example corresponds to V equals 1 over root 2, 1, negative 1, 1, 1, and lambda equals 4, 0, 0, 1, or something like this. So this is telling me, the V, that I am rotating from my original coordinate axes. I'm rotating it around, so now I'm in a new coordinate axis that, so I could think about this as my first V direction, and this is my second V direction. So maybe I'll just call that V1 and V2. So I've rotated to this new coordinate axis. And then in this new coordinate axis, I've got a spread or a variance of 4 in that first new axis direction and a variance or a spread of 1 in the second new variance direction. And so the concepts that we looked at before for diagonal covariance matrices still apply. It's just that instead of looking at the diagonals of sigma like we did before, we're now looking at the diagonals in V, or rather the eigenvalues of our covariance matrix to tell us how much spread there is in different directions. And V is now telling us what those directions are. So the directions where we have this spread might not be the original x1 and x2 directions, but rather they correspond to some rotation that's dictated by the eigenvectors V. Okay, are there any questions so far? Yes?
So V1 here will also correspond with sigma and select.
Right, that's a great point. So if I were to draw a large number of samples from this distribution, right, what I would expect to see, first of all, is that basically I'm going to have most of my samples concentrated around the origin, but the spread of those samples is going to follow where these contours are. Now if I were to do PCA, for instance, on those samples, then the first principal component direction is in fact going to correspond to V1. So they won't be exactly the same because we do PCA with a finite number of samples. And when we talk about the mean and covariance of a distribution, that's for effectively an infinite number of samples. So the first principal component direction and the eigenvectors of our covariance matrix here are not exactly the same because one's computed with finite samples and one is for the whole distribution. But they correspond to one another, and as the number of samples we get goes to infinity, then the first principal component goes to this first eigenvector of our covariance matrix. Yes?
What would the sigma matrix look like in the case where it's not like symmetric, the distribution, where you've got like maybe it's like a weird shape?
Within our expression for the distribution function, we have sigma inverse. So by construction, sigma has to be invertible. And as we talked about later in the quarter, or earlier in the quarter, that means that it needs to be a positive definite matrix. So we do not have asymmetric or non-positive definite sigma matrices for a valid Gaussian distribution. If you wanted a distribution where, I don't know, let's just say back in 1D, right, where it's the distribution is not symmetric, where it looks different on one side of the mean than the other, then it's not a Gaussian. You would need a different model than what we're describing here. Yes?
Are the sigma matrices that
So when we're talking about a covariance, are we talking about the covariance between the features or between the samples?
We're talking about the covariance between the features.
Okay.
Right. So in this example, for instance, right, what this is telling me is that if I were to observe a vector x1, and I tell you, oh, x1 is really big, then you know that x2 is more likely to be really big as well, right? And you know that because of the covariance matrix. And that's true for each sample independently. So here we're imagining, what we're going to be doing is we're going to imagine that we have a collection of samples that are all independent draws from the same distribution, and the covariance matrix is telling me how the different features within the samples are related to one another. All right. So moving closer to the EM algorithm, there's two things that we need to do before we can get back to clustering. First, we need to say, given a collection of samples, how do we estimate sigma and mu? How do we estimate the parameters of that distribution? And second, everything here doesn't really have any notion of clustering. We're going to have to start talking about mixtures of Gaussians. Okay, but before we get to that, let's just talk about maximum likelihood estimation. Okay, so we are going to be given a collection of points, xi, all p-dimensional, for I equals 1 to n. And we want to know if we were to try to fit a Gaussian distribution to these samples, if we were going to try to find the Gaussian distribution that best fits this data, then how do we do that? So in other words, we want to choose the values of mu and sigma so that the likelihood of observing this collection of points, xi, from I equals 1 to p, is maximized. Right, so if I had a collection of points and they look like this, and then we say, well, what is the mean and covariance of that data? And we look at a Gaussian distribution whose contours are like this, well, this wouldn't be a very likely collection of points to draw from this distribution. So what we're trying to do is we're trying to find the parameters of the distribution, the mu and the sigma. So in this example, maybe my mu is there and my sigma is like this, that maximizes the likelihood of the samples coming from that distribution. So more formally, what we mean is that we are going to choose mu hat and sigma hat as the arguments that mu and sigma that maximize the likelihood. And by the likelihood, what I mean is we are going to assume that all of the samples are drawn independently. Once I draw one of the xi's, it doesn't affect what the other xi's are. So we're going to look at the product of this distribution function p evaluated at each xi. We're going to look at the likelihood of each xi, where this likelihood function has parameters mu and sigma. Okay, so for each xi, we're saying how likely is it, or what's the value of this distribution function for a given mu and sigma. And then we are going to compute the product of these values across, over all p different samples. Now, to simplify things, we can say, well, this is the same, really, as maximizing the log of this expression of the product from I equals 1 to p of xi mu sigma. And this is the same as, we just generally like working with minimization problems. So this is the same as minimizing over mu and sigma, the negative log. And so we can we can pull the product outside of the log to make it a sum from I equals 1 to p of the negative log of this p of xi with parameters mu and sigma. Okay, so we want to find the values of mu and sigma that minimize the sum of the negative log likelihoods here. And now what we can do is we can plug in our expression for this distribution function that we wrote right here. This is working out really well. So I'm going to erase part of this. And so we can say that our mu hat, sigma hat, is equal to the argument. All right, it's not working out so well. Of the sum from I equals 1 to p. And now we're going to take the negative log of this expression. So we are going to have 1/2 log determinant of sigma plus p over 2 log 2 pi plus 1/2 xi minus mu sigma inverse xi minus mu. So all we've done is computed the negative log of this expression here. Yes, there's a transpose missing. Thank you. Okay, so if we were to try to solve this optimization problem, then we would get the following. And we're not going to derive it here in class, but what we are going to have is that the mu hat is exactly what you would hope it would be, 1 over n, sum from I equals 1 to p of the xi's. So we just compute the average of all the data we have, and that's our best maximum likelihood estimate of the mean of the Gaussian distribution. And sigma hat is going to be 1 over n times, okay, I'll try to make the sum a little bit different than sigma here. The sum from I equals 1 to n of xi minus mu times xi minus mu transpose. So it looks like a complicated optimization problem. You can work out relatively straightforwardly the optimum value of this for the optimum mu and the optimum sigma, and it works out to be exactly these equations. So very straightforward to estimate the mean and covariance from a collection of samples. Yes?
Just to clarify, what are the n's and p's again?
So each xi is in a p-dimensional space, and I goes from 1 to n. So n is the number of samples we have, and p is the dimension of the samples. Okay, so all of this has been, well, it's useful, but it feels far from clustering. Because with clustering, we don't imagine all of our samples are collected together in a blob, but they could be more spread out. We could have multiple blobs. And so now we are going to talk about Gaussian mixture models. Okay, so first of all, let's just make a little illustration. So in 2D, it's where my drawings are best. So we could imagine having a Gaussian distribution here and having samples from that. And let me get a few more colors. And we could also imagine having, let's say here, another Gaussian distribution with contours like that. And maybe over here, here's a third possible Gaussian distribution. So now you could imagine that you have, you're drawing your samples by saying, well, with probability, let's say pi 1, we are going to draw from the white distribution. Let's just say white. And then with probability pi 2, you're going to draw from the blue distribution. And with probability pi 3, which is going to be equal to 1 minus pi 1 and minus pi 2, so if we don't draw from white or blue, then we are going to draw from the red distribution. Okay, so what we're saying here is sort of like we're going to flip a 3-sided coin, And depending on how that coin lands, we're going to draw either from the white Gaussian or the blue Gaussian or the red Gaussian. So together, this still makes up one full distribution with its own sort of contours that would look something like this. Okay, so here is a distribution now where there are multiple different modes or peaks in the distribution. So this is not Gaussian. We're thinking about this because these different modes or peaks could correspond, for instance, to cluster centers. So if we've got a bunch of data and we want to cluster it, we could model it by saying, well, imagine that it comes from a mixture of Gaussians, something like this. Now, when we draw our samples, we don't know which sample is coming from white, which sample is from blue, and which sample is from red. All we're getting is a bunch of different samples scattered all throughout here. And from them, we want to, effectively, what we're going to do with the EM algorithm is to perform clustering by figuring out what these different Gaussians are, what is the mean and the covariance of the white, of the blue, and of the red Gaussians. And then for each sample, we can say, well, which Gaussian is it closer to, or which Gaussian is more likely to be responsible for this sample? And we can use that to perform clustering. Okay, so first of all, does the notion of a Gaussian mixture model make sense? Yeah.
So what we're doing is that given the data distribution, we want to estimate the distribution of the white, blue, and red.
Okay, so we're going to talk about estimation in a second, but you're right, that's where we are headed. For now, I'm just trying to describe the distribution. So maybe what I'll try to say more explicitly is if we've got a Gaussian mixture model, which I'm going to abbreviate as GMM, with capital K components, then I'm going to let pi little k equal the weight on the kth component. So how likely it is I'm to draw from that Gaussian in general. And we are going to assume that each of these pi k's is a probability, so each one is greater than 0. And if I were to sum all of these pi's across all capital K components, they have to sum up to 1. We also are going to have mu k, which is equal to the mean of the kth Gaussian. And we are going to have sigma k, which is equal to the covariance of the kth Gaussian. And so now what we can do when we think about drawing samples from this distribution, what we would do is first choose a component k with probability pi sub k. And then, once we've chosen a distribution, we are going to draw xk from the Gaussian with mean mu k and covariance sigma k. So now what we're going to do is we are going to say, imagine that I've got a collection of n different samples that are drawn from this mixture of Gaussians. So each sample is coming from this process where we chose some component with some probability, and then we drew from the corresponding Gaussian distribution. So what we'd like to do is to estimate these three things what the weights are, what the means are, and what the covariance are. And if we can do that, if we can basically take our data and figure out that the underlying distribution looks something like this, then we're going to be able to use that in order to do some clustering. Yes?
So basically the white graph like on the bottom, so like the contour plot.
Yeah.
So each point on this plot is actually the weighted summation of the probability of each of the Gaussian distribution probability.
Right. So if I wanted to write down the distribution function for the Gaussian mixture model, which is I think what you're asking for, then we can use exactly the parameters that I just outlined. So now if I have a particular sample X and I want to say how likely is that X under this distribution, or what is P of X, then what I would do is I would compute this as the sum from K equals 1 to the number of Gaussian components of pi sub K and then P of my point X with Gaussian K, with mean K, mu K, and covariance sigma K. So if I've got K Gaussians, I compute the likelihood of my point under each of them, and then I would compute a weighted sum of those values in order to get my P of X for the mixture model. Yes?
Can you explain the difference between, I guess, is the P of X that you just wrote, that's, how is that related to P of X on the top middle slide?
So this is corresponds to the distribution for one Gaussian with mean mu K and covariance sigma K. This is the distribution function of the Gaussian mixture model. So, and more generally, if we have a collection of data and we want to describe the relative likelihood of different values of the data, we come up with a probability distribution to describe it. One distribution is just a single Gaussian, and that's what we wrote the distribution function for earlier with the Gaussian. And another candidate distribution function is the Gaussian mixture model. And then there's many, many other distribution functions out there. These are just two particularly important ones to know about. Yes?
On the top side, is the product of the likelihood to n?
Oh, thank you very, very much. Oh, yes. I apologize. I've got a typo that I think propagated for multiple boards. Okay, we are maximizing the likelihood over all n samples. Product is over all n samples, n here. And then if we go back over to here where we had this expression for the maximum likelihood problem, we're again looking over all n samples. I'm sorry for that. Thank you very much. Yeah, any other questions? Yeah.
So when we're talking about components here, you mean like the white, the red, and each one of those example distribution components?
Yeah, that's exactly right. Great point. So in this example, we've got K is equal to 3, And so, for instance, let's just say that this is 1, let's just say that this is 2, this is 3, this is 5, and this is 2, and this is 4, and this is 8. Okay, so then we would have mu white here would be equal to 2, 2. And mu blue in this example is equal to 4, 5. And mu red in this example is equal to 8, 3. And then I'm not going to write down covariance estimates, but yeah. So these are the components, and they each have their own separate mean, and they each have their own separate covariance matrix.
K is 3 or
Oh, jeez, yeah. K is 3. Yeah.
So here we also don't know what K is. That's also along with we don't know what mu and the covariance is. So like, does that introduce more or less error compared to like K clustering where we only don't know?
Okay, great question. So we talked last time with k-means. Well, what happens when you don't know the right value of k? And we talked about how there's lots of heuristics for trying to choose a good value of k. That same challenge arises here as well. So in general, we're just handed a collection of samples. We don't really know what the true value of k, capital K, is, and we have to estimate it. For this class, and as we talk about the EM algorithm, we are going to assume that we do know capital K. And so given capital K, how do you do clustering? How do you estimate all the means, covariances, and weights of the Gaussians? And then once you know that, then you can figure out some kind of wrapper to put around it to figure out a good value of capital K. So we're just going to say, given a good value of capital K, how do we proceed? Yes?
For the mu hat on the middle board, should that be the sum of n multiplied or
For mu, oh, this one too. Yeah. Gosh, boy, I'm sorry. I'm just really brain dead today. Yes, thank you very much. Yes?
how do you find the weights of K?
The pi case?
Yeah.
Oh, okay, this is where the EM algorithm comes into play. So we haven't talked about that yet, and that's what we're going to do now. So, perfect question. Okay, so all of this is just about describing a mixture of Gaussian's distribution. Now we're actually going to finally get to estimation. Okay, so given a whole bunch of different points, in p dimensions from I equals 1 to n, we want to estimate the collection of pi k's, mu k's, and sigma k's for k equals 1 to capital K that maximize the likelihood So in other words, what are the parameters of this Gaussian mixture model distribution function that maximize the likelihood of me observing this collection of xi's? Okay, so this is our goal. And so with this algorithm, we are going to start with initial values of all of these different parameters that we are trying to estimate. And I'm not going to indicate the, iteration. So we're just going to have initial values of all of the pi k's, mu k's, and sigma k's. And we are going to start using our data to improve on those estimates. So within this method, I think I'm just going to skip the middle board altogether here. We're going to go back and forth between two steps, an expectation step and a maximization step. So first we've got the E step, where E is for expectation. And what we are going to do for the E step is first we are going to compute what I'm going to call P little k xi. And this is going to be the probability that xi was drawn from the kth Gaussian. So in particular, we mean that this is equal to, I'm going to use capital P for probability. And remember last time with k-means, we let ki be the cluster that we associated with point xi. So we're saying what's the probability that xi is drawn from Gaussian k, given, well, the values that we observe in xi. And so to compute this, we need to look at the following expression. So first, we look at the probability that we have drawn from the kth Gaussian at all. Like, what's the likelihood that we're using the kth Gaussian period? Because some Gaussians have more weight, pi, than others. And then we are going to look at the likelihood of our point xi, given that it comes from the kth Gaussian, and divide by just the likelihood of that point at all. So this is an instantiation of something called Bayes' rule. It's a core concept in probability and statistics. And we're not going to go into it in detail today. Well, actually, I guess the rest of this quarter now, huh? But this is something I'm going to ask you to take on faith here, but it is something that you can look up, and the basic idea is very simple. And we can simplify this now, or use some of the information that we have. So this probability that we are using the kth Gaussian period is simply what we've been calling pi k. And then we've got this likelihood here, the likelihood of xi, given that it came from the kth Gaussian. And so now we can use our distribution function with means mu k and covariance sigma k. And then in the bottom here, where we're just saying what's overall the likelihood of xi for the overall Gaussian distribution, what we would do is we would sum, over all the different Gaussian components. So now I'm going to use k prime from 1 to capital K of pi k prime p of my sample xi with Gaussian mu k prime covariance sigma k prime. Okay, so this is given our current estimates of the means and the covariances and the weights of all the Gaussians. I can straightforwardly compute these values, these probabilities that I drew xi from the kth Gaussian as opposed to all the other Gaussians in my mixture. Once I have this, then I can, well, first let me just say that this thing here, which I've been calling P sub k of xi, sometimes in our book and in the literature, people will call this the responsibility that Gaussian component K takes for sample or data point xi. So to just give a small illustration, we'll just move over to the other board. Okay, I just want to give a tiny little illustration down here in the corner. So imagine that I have two different Gaussians. One is here and the other is here. And then imagine that I draw a sample that's right here. So you might ask, well, what's the likelihood that it came from this Gaussian or this Gaussian? And so you could imagine that we would say in this case, well, both of these Gaussians have roughly equal responsibility for this sample, right? And in contrast, if we had a point over here where the star is, then we would expect this Gaussian here to have much higher responsibility for this sample than this one. Because, assuming that these two Gaussians have equal weight, step out of the sunlight here, the likelihood of this sample coming from this Gaussian distribution is relatively high compared to the likelihood of this sample coming from this Gaussian distribution. Okay, so once we've computed all of these responsibilities for all of our samples and for all of our Gaussians, then we turn to the M step, where M is for maximization. And in particular, what we are going to do is essentially use these responsibilities, the PKXIs, to update our estimates of all the different parameters, the pi k's, the mu k's, and the sigma k's for k, little k equals 1 to capital K. And so in particular, our new estimate of mu k is going to be inspired by what we did when we said we wanted to estimate the mean for a single Gaussian. So if you remember, what we did there is we were computing the average of all of the different xi's. But now what we want to do is we only want to estimate the mean of one of the Gaussians in this mixture component. So what we're going to do here is we are going to weight our xi's using these responsibilities. So in particular, we are going to sum from I equals 1 to n, this responsibility pk of xi times xi. So when we're trying to compute the kth mean, we're going to give more weight to the xi's where the responsibility for the kth Gaussian for that point is higher. Now, when we're doing these weighted averages, we want our weights to sum to 1, so I'm going to now add a little normalization factor here, which is simply the sum for j equals 1 to n of p, k, x, j. So this is like saying, let wi be equal to pk, or wik, I guess, be pk of xi divided by the sum j equals 1 to n pk of xj. And then my mu k is just equal to a weighted sum with weights wik xi. So I'm just doing a weighted sum of my samples where I've got bigger weights for the samples that are closer to or where there's more responsibility coming from the kth Gaussian. And I've normalized these weights so that the weights sum up to 1. Okay, so that's how we would update our estimate of mu. Similarly, we are going to update our estimate of sigma for the kth Gaussian by simply looking at, again, before we were looking at the average of the xi's minus the means, outer product with each other, like this. So now what we're going to do is we're just going to use our estimate of the means, the mu k's, and we are going to compute this weighted average just like we did before. So we are going to have the sum from I equals 1 to n, and again we're going to have this weight wik. So instead of doing a regular sum, we're doing a weighted sum to estimate the covariance matrix for each one of our Gaussians. And then finally, we need to estimate our pi k's, the weights for each of the Gaussians. And for that, we are going to look at the sum from I equals 1 to n of pk xi, these responsibilities. Okay, so within this algorithm, what we are doing is then, with the EM algorithm, you would alternate between the E step and the M step. Okay, so we would set some initial values of our Gaussian parameters, of the means and the covariances and the weights. And then for each iteration, we would first do this E step. We would estimate all of these responsibilities. We would basically figure out how well associated each sample is with each of the Gaussian components we've estimated so far. And then given that information, we would go back here and we would perform the M step and update our estimates of the means and the covariances and the weights. Okay, so there's more details in the online lecture notes, but I want to just talk a little bit about what's happening here, how it relates to the k-means algorithm, and why it can be preferable in some settings. Okay, so first of all, what it's doing is it is tracking or estimating both means and covariances of the clusters. So if we think back to this kind of Mickey Mouse example that we had at the beginning, this is an example where the EM algorithm can yield good clusters while the k-means algorithm cannot, in part because for each of these clusters, we're going to have a different covariance. So we aren't assigning points to a cluster only based on distance to the cluster center, but also based on how wide or how much variance there is within each cluster. So let's talk about that in a little bit more. So we are effectively measuring the distance from xi to a cluster k xi minus mu k transpose sigma k inverse xi minus mu k. Versus in k-means, which is using xi minus mu k, just the Euclidean norm distance squared, which is xi minus mu k transpose xi minus mu k. So with k-means, we were just looking at raw Euclidean distance between the cluster mean and each point. And that's why I was claiming that you would have points like this one here, for instance, that with k-means would be associated with this cluster instead of the big cluster. But with the EM algorithm, what we're effectively doing is measuring the distance from each point to a cluster in a way that's modulated by this covariance matrix. So it's taking into account, so if we again look at the same point, but think about which of these three Gaussians is responsible for it, there's some non-trivial responsibility for this point coming from this center Gaussian because it's got a big covariance. So this distance here that I've drawn is something that shows up in a lot of different parts of machine learning. It's called the Mahalanobis distance, where you are effectively, like I said, modulating your distance measure using this notion of a covariance matrix sigma in the middle of it. And the reason that this can be useful, for instance, is the following. If I go over here, okay, imagine that I've got points like this. Okay, and now I've got three different points, X and Y and Z. Okay, so now if I were to look at just Euclidean distance, then the distance between X and Y is about the same here as the distance between X and Z. But if I were to have a Mahalanobis distance that's based on sort of the covariance structure of all of my samples here, so if this sort of covariance structure led to some matrix sigma, then if I were to look at X minus Y transpose sigma inverse X minus Y, then that Mahalanobis distance is going to be much smaller than the Mahalanobis distance between X and Z. And that is, in fact, what we might want in a lot of these clustering settings, right? Even though these points, X and Z, are just as close together in a Euclidean distance sense as X and Y, when it comes to clustering, we really want to make sure that X and Y are in the same cluster because they're close relative to the geometry and spread of the data. Whereas we're less concerned about whether Z is in the same cluster as X. Okay, the final thing I'll just mention very quickly, I mentioned at the beginning that the EM algorithm gives us soft clustering. So basically up at the top here, we computed all of these responsibilities. And so if you really just wanted now to assign clusters to points, what we can do is for each point, we can talk about for all the different Gaussians or all the different clusters, what the corresponding responsibility is. So a point might have a set of responsibilities where one of them is really huge because it's very close to the center of that Gaussian. And in contrast, we might have those responsibilities sort of spread out across multiple Gaussians, reflecting that we can't really tell which Gaussian it came from. And that's what gives us the soft clustering result, this vector of responsibilities, of k responsibilities for each sample xi. Okay, thank you all so much. It's been a pleasure working with you all quarter. I've really appreciated all the challenging and thoughtful questions you've asked. Have a good final and a great winter break. Thank you very much.